My pleasure to introduce to you Dowker. Studied PhD from University of Cambridge under the supervision of Stephen Caulking. She went on to become a postdoc at Penrose in the United States, followed by University of Santa Barbara, California, and Caltech. And she's currently a professor at Imperial College in England. And she has been a pioneer in one of the approaches to quantum gravity, the so-called causal set. And we believe that she will tell us throughout the video. And without further delay, I leave the floor to her.
Thank you, Causal. Thank you also to you and the other organizers for this nice workshop, for inviting me to give these lectures. It's a real pleasure to be lecturing in person again. I get a bit kind of disoriented sometimes because it's been such a long time, so I'm better out of practice with lecturing in front of a live audience. So if I kind of look in the wrong direction or something, it's just because I'm wondering whether you're all really there, or you're just some virtual thing. Anyway, we'll see how it goes. So thanks for sticking with it. I'm going to try and make things less technical, although I did pack this with a few theorems, this lecture, and more kind of conceptual, intuitive, sort of more fun things to do at the end of the day. You've been working hard at the workshop, at the conference, so hopefully this will be enjoyable and stimulating. So the motivation for discrete Lorentzian geometry, and in the particular example of discrete Lorentzian geometry that I'm going to tell you about, causal sets, is quantum gravity. That's the physics motivation for me. But I think that they have an intrinsic interest in themselves. You may just be interested in them as some kind of approximation, if you like, to Lorentzian, to continuous Lorentzian, continuum Lorentzian spacetimes. But for me, the physics is the other way around. The discrete entity is the real thing, the physical thing, and the continuum is an approximation to it. So the approach, this causal set approach to the problem of quantum gravity, was suggested, arose independently, was suggested independently by three groups in the late 70s, early and in the 80s. And the physics of causal set theory as an approach to the problem of quantum gravity has three main aspects: as kinematics, which is just what a causal set's like. Is it possible, this conjecture that continuum space-time can be an approximation to a fundamentally discrete thing? Does that hold water? Does that make sense? What's the evidence for it? And then there's dynamics, which is what are the laws of motion, if you like? What are how does it behave? And do these causal sets actually arise in a dynamical theory, in a dynamical way? And then finally, there's phenomenology, which is what evidence do we have for this, for such a hypothesis, physical hypothesis? So I'm not going to say anything about dynamics, nothing about phenomenology. These three lectures are going to be about kinematics of causal sets. And these are some overarching kind of themes. A causal set is a combinatorial entity. It is actually literally a transitive directed acyclic graph. So there's combinatorial data only. Another theme that runs through all the lectures is the contrast between Riemannian and Lorentzian geometries and discrete geometries. And I want to highlight something which Renata Loll is going to give a talk about, a Riemannian discrete geometrical geometry. So I want to highlight her talk. And then there's this theme, which you'll see, of non-locality versus locality. I won't say anything about that now. I don't want to steal my own thunder, but you'll see that this is going to come up. So that's a theme. And then I'm working my way towards a definition of Ricci scalar curvature for a causal set, and that, you know, by 5 o'clock on on Friday, you know, we may get there if you're all still with me. Okay. Right, I'm not sure. I can't advance this using this now. Oops, well, that worked. Okay. Oh, and just before I leave kind of overarching themes, here is a couple of quotations from the Riemann's inaugural lecture, in which he kind of, you know, lays out the foundations of what we now call Riemannian geometry. So for Riemann, it's a strange thing. He seems to imply that, well, discrete manifolds, we all know about them. There's no problem with them, you know. That's all fine. But continuous manifolds, now they're really weird. You know, that's strange. We've got to figure out what's going on there. So, and he makes these comments. So, the first one is, for a discrete manifold, the principle of its metric relationships is already contained in the concept of the manifold itself. Whereas for a continuous manifold, it must come from somewhere else. And of course, we see that because you put the metric lives on the manifold. So, you know, there's a hierarchy of structures that you have to define. And the manifold comes first, and then the metric is imposed on top. Therefore, either the reality which underlies physical space must form a discrete manifold, or else the basis of its metric relations must be sought for outside it in binding forces that act on it. And then he also says definite portions of a manifold distinguished by a criterion or a boundary are called quanta. Their quantitative comparison happens for discrete magnitudes through counting, for continuous ones through measurement. And I'll refer to Riemann a bit later on. Okay, so here's the plan. I'm actually, I've chosen the wrong coloring for my slides. You can't see the titles. So that says plan of lecture 1. So first I'll define a causal set, which is a discrete order or transitive directed acyclic graph. I will state the discrete continuum correspondence. It's a proposal, a conjecture, if you like, and the Hauptvermutung or central conjecture of causal set theory that goes along with this discrete continuum correspondence. So that states when, under what circumstances, we can say that a Lorentzian manifold is a good approximation to a causal set. I will then, and the center of this lecture is to promote to you a theorem which I now, after many mistaken kind of misunderstandings on my part and misreadings of history, I've now come to think of as the Chronheimer Penrose Hawking Malamute Theorem. And it's a theorem in the continuums, nothing to do with discrete anything. So the ground on which, and it's the basic reason that we have confidence that the underpinning of a Lorentzian manifold can be a completely combinatorial discrete thing. So the ground on which the discrete hypothesis rests is a continuum theorem, and yet in the physics we are proposing that underneath the continuum, the more fundamental layer of reality, if you like, is discrete, and the continuum is a higher level in approximation to it. Okay, and I'll give it, if I get to the end, I'll give a little illustration of a little example that illustrates what I mean by being able to deduce continuum geometrical information from a discrete entity like a graph. Okay, right. So a causal set is a transitive directed acyclic graph. So it's another, and so there's lots of synonyms for it. There's another one is locally finite partially ordered set, or locally finite poset for short. And sometimes we shorten causal set to corset. So the order relation is irreflexive. It's transitive. So if x does not precede x. If x precedes y and y precedes z, then x precedes z. And those two axioms are make C into a poset. So those are the axioms of a poset, the definition of a poset. And we add this local finiteness condition, which is that if you take two elements x and z, which are ordered, so x precedes z, the cardinality of the set of elements y, which lie in between x and z in the order, is finite. So it's local finiteness. So sometimes there's a need to think of a concrete C, a concrete set. And if we do need to do so, then we can just assume that C is a set of integers. And that the integers satisfy this consistency condition, so that if x precedes y in the order, then the integer x is less than the integer y. Okay, so that's a sort of consistency condition. Sometimes that's called a natural labeling. Yes? It means it's not fine. It's not a finite set. It can be an infinite set. Yeah. Okay. Right. And then a super useful way to draw or think of causal sets is as a Hasse diagram of the graph. So just like the diagram of graph, the nodes represent the elements, the edges are represented by straight lines. So here the ordered pairs of the relations, the pairs of elements that are related in the order, they are represented by lines. And there is a convention that the order, the direction of the order, is represented by up and down. So here's a causal set. 0, 1, 2, 3, 4, 5, 6. And it's a transitive graph. So that means, 0 precedes 3 and 3 precedes 5, but I don't need to draw on the edge between 0 and 5 because it's transitive, and therefore it's implied by the edges that I have drawn. So the Hasse diagram is the graph of the so-called transitive reduction of the partial order. And what else? Okay. And yeah, so the direction of the order is implied by what's above and what's below on the page. And in fact, mathematicians use those terms. Mathematicians who study partial orders, they use those terms above and below. And it's such a fantastic thing that mathematicians have chosen the same convention as relativists, that the things that are earlier, that precede, are down here, and the things that are later, that are preceded by, are up here, because otherwise, talking to the mathematicians who study orders, you'd have to be doing this all the time. So it's great. So this is the past, this is the future. Okay. Physically, continuum space-time is supposed to be an approximation to a causal set. Of course, not one with only 7 elements. In fact, if the discreteness is physically on the order of the Planck scale, then in our observable universe, the causal set that would be the underpinning of our observable universe, there would be roughly 10 to the 240 elements in it. So this is nowhere near representative of a physically interesting, meaningful causal set. Oh, I'm sorry, that means it's a note to me to go to the blackboard. Yeah. Yeah, this fantastic mathematician, physicist, BB. No, it's just yeah. Oh, and another physical concept, idea, thought is that only the equivalence class of the order is physical. So I could write the same order draw the same order, but just label it in different ways. So I could have 0, 1, 3, 2, 5, 4, 6. Of course, because I'm imposing this condition, this natural labeling, I'm not free to label these any old way. So, but nevertheless, this is different labeling to this one, but they're order isomorphic. So there's a bijection between them that preserves the order, and physically, the concept is that these are the same physically.
Let me ask one more question.
Yes.
So I only care about the ordering within the graph, right? I mean, whether you make a long edge that has 3 below 2 or a short edge that has 3 above 2 has no bearing on the second value.
Say that again. I mean,
sorry, I only care about the graph structure. I don't
yes.
care about where the things are positioned on the graph.
Correct. Yeah. Except for this above and below.
If we shorten the edge of 3 on it, so the 3 was above 2 on the black, that would still be the same.
Yes.
Yeah.
Yes. Correct.
Just another question.
Yes.
So if you don't have decorations like length on the edges, will this be? I mean, you have to have some correspondence for volume. Is this the number of? Okay.
Yeah. It is, but you're anticipating me. Good. So it's purely combinatorial. It's just graph structure. There's no decorations on it. Yeah. Okay. There's lots of terminology from partial orders that we can use and which are super useful. So a chain is a subcausal set which is totally ordered. So the subcausal set that consists of 1, 3, and 6, that's totally ordered. There, 1 precedes 3 and 3 precedes 6, so that, and 1 precedes 6. So it's a total order. So a chain is a totally ordered subset. It doesn't need to be a maximal chain. So 1, 3, 5, and 6 is also a chain, but it's a maximal chain. But a chain doesn't need to be maximal. An anti-chain is a totally unordered subset. So 1, 0, 1, and 2 is an anti-chain. 5 and 4 is an anti-chain. So upsets are, if you like, future sets. They're sets, subcausal sets which contain every element which is above any of the elements of the set. So an upset could be 2, 4, 6, 3, 4, 5, and 6. That would be an upset. A downset is similar, just replace up with down and to the future, or above with below. So a downset would be 4, 3, 0, 1, and 2. But 4 and 2 is not a downset because 4 is above 3. So you need to, so anything that contains 4 and is a downset must also contain 3. Yes. Yes. Good. So yes, thank you. It's a directed graph. I could write these on there, but that's redundant given the convention of a Hasse diagram. So the direction is implied by just position on the page. But yes, I could, I could, yes.
I have a question about the definition of anti-chain. So
yes.
As an example, 0, 3, 2 on the left here is not an anti-chain, right?
Correct.
But with 0, 2, 3 an anti-chain. So still no.
No, that's not an anti-chain. Because there's a relation between 0 and 3.
It doesn't matter where they are when I'm listening.
No, it's just a subset with the induced order relations. Yeah. Okay. Minimal element. There's only one maximal element, that's 6, and there are 3 minimal elements, which are 0, 1, and 2. Yes, interval. So there's 2 concepts of interval. So there's the inclusive interval, which is if x precedes y, then the inclusive interval between them is the set of all z such that x precedes or equals z precedes or equals y. And of course, then there's the exclusive interval, which is z such that x precedes z, which precedes y. Okay. Covering, good. So mathematicians call any of the relations or edges that are drawn in the Hasse diagram covering relations. We tend to call them links. Same, it's a synonym, and it's a relation in, it's an order, it's a relation in the order which is can't be implied by transitivity from any other relation. So it's the ones that appear in the transitive reduction. So they're the sort of nearest neighbor relations, if you like, in the graph. So there's a link between 2 and 4, or you can also say the pair, the set 2, 4 is a link or a covering relation. 2, 6 is not a link. It's not a covering relation because 4 is in between them. Okay, I think that's it. I'll put those up there. So this is just a note to myself because I fell over on this issue and got very confused once. So I just want to point out that when mathematicians talk about lengths and volumes, they have no units, but physicists have units. And whenever I mention space-time, what I mean is a causal Lorentzian manifold, smooth. And for a causal Lorentzian manifold, the space-time causal order J minus is equivalent to a partial order. So we can define, so for continuum MG, we can define x precedes y if x is in J minus of y and x is not equal to y. Then so J minus contains, it's essentially equivalent to a partial order. You can say it's a reflexive partial order, which I'll use the same notation, this precedes symbol, both for causal sets and for manifolds, Lorentzian manifolds for spacetimes. Hopefully, so it should be clear in context which one I'm using. When you can go through and put little subscripts or superscripts on everything to make sure that you're clear which set you're talking about, but I'm not going to even bother. Okay, and that is called the causal, sometimes I call it causal order, causal relation, and it's the familiar J minus from Lorentzian, continuum Lorentzian geometry. So, yes. Oh yeah, I think I put it in, so a stem is a finite down set. Yeah. I was going to talk about stems, but I think I actually don't, but anyway. Yeah. Okay, and we can define these objects. So for the continuum, now we can define the inclusive interval, inclusive causal interval. I think people have been calling those causal diamonds. You can define the exclusive causal interval, but there's a new thing which exists in the continuum, which doesn't exist in the causal set, which is the Alexandra interval, which is defined to be z such that, so z in M, such that x is to the chronological past of z, which is to the chronological past of y. So that's the Alexandra interval. It's an open set. Okay, so there's no analog of this in the causal set, so in the discrete case. Okay. Yes, that's it. Okay, so this is a proposal for a correspondence between causal sets and continuum spacetimes. And it's a proposal and it's a proposal of how you can recover the continuum, how the continuum spacetime and the causal set are related to each other. Okay, so the causal set is well approximated by a spacetime, Lorentzian manifold, if there exists something which Bombelli et al. Call a Planck scale faithful embedding. That is an embedding from the causal set into M that satisfies the following conditions. It's uniform at the Planck scale. So the number of causal set elements embedded in any sufficiently large, nice region is approximately equal to the space-time volume of the region in fundamental units, volume units, space-time volume units. So that means that so we have M, an embedding of this graph into M. So I'm just drawing the points that are embedded. And if you take any sufficiently large and not grotesquely wiggly region, then and count the number of elements that are of the causal set that are embedded in there, then that should approximately equal the volume of the, exactly as you anticipated. So the number gives you the volume, the counting measure is the volume measure. Okay, and it's order preserving, so that if you have in the causal set, let's say X, Y, and Z, then the map phi takes you to phi of X, phi of Y, and phi of Z. And if X precedes Z, then if X precedes, Y. So X precedes Z if and only if phi of X precedes phi of Z, and X is unrelated to Y if and only if phi of X. I think I didn't need to say the second thing. If and only if phi of X is unrelated to phi of Y. So order preserving and Planck scale uniform. And then there's a sort of, this can only possibly work condition, which is that the distance over which the continuous geometry varies is everywhere much greater than the discreteness length or time scale. So if your geometry has, if this geometry M has teeny little wormholes, which are much, much smaller than the discreteness scale, the discreteness obviously is not, the causal set, the discrete entity is obviously not going to tell you anything about those. So there's some condition here which says that this has got to make, it's got to make sense. Okay. Right, so does this hold water? This?
So when you say this is over which the geometry varies, does that mean like perfect?
Yes, exactly. Yeah. Yeah. So all the, all the distances and all the different directions that the curvature will give you. Yeah. Yes. Square root. Correct. So phi of X precedes phi of Z means that phi of X is in the path light cone of phi of Z, right? In or on the path light cone. Yeah. So when I talk about the order in M, then I'm always talking about the space-time causal order. Yeah. Okay.
You tell us what is sufficiently large, nice, and
No. No. Okay. All right. So does it make, can continuum geometry at large? So what does the discrete continuum correspondence say? It's claiming that continuum geometry at large scales, sufficiently large scales, can be encoded in this causal set, this completely combinatorial discrete entity. That's what it's claiming. And the thing to bear in mind here is the continuum approximation to a molecular state that is a fluid. You know, a fluid has say a density function, but we know that really the fluid is made of molecules, so there's really discrete. It's really a discrete molecular state, but the fluid description is an approximate description on large scales compared to the intermolecular size. Okay, so that's the concept to bear in mind. Okay, so the discrete continuum correspondence can only hold water if this central conjecture, Hauptvermutung, holds, which says that if you have a causal set and you can faithfully embed it in two manifolds, M1 and M2, then those two manifolds had better be the same. They'd better be essentially the same up to kind of things which don't really matter. They're so small, or they're on scales that are so small that the large scale geometry just doesn't see it, doesn't care. In exactly the same way that if you have a molecular state, a particular molecular state, you could have two different fluid descriptions, vary just slightly in a completely irrelevant way, right? So the idea, so to make this precise, which is part of the work that goes on, of course, we need to define approximately isometric. So there is work in this direction which is trying to define or construct and use and justify a Gromov-Hausdorff distance between on the space of Lorentzian manifolds. And there's also a possibility that we can actually use causal sets and the concept of faithful embeddings to define a distance between continuum spacetimes. And the example is what I've called the Bombelli distance, and I hope to describe that to you in the second lecture. Okay. All right. So where does our confidence that this is even plausible come from? So it comes from several things by now, but the one main source of confidence is a theorem in the continuum. So this is now I'm going to leave causal sets, leave anything discrete behind. And the theorem is the Chronheimer, Penrose, Caulking, Malamute theorem. And it says that if you have two distinguishing spacetimes, M and M prime, and they have dimension greater than 2, and if you have F, a causal isomorphism between them, that means that you have a bijection, F is a bijection, and it preserves the causal order. So X precedes Y if and only if F of X precedes F of Y. Then F is a smooth conformal isometry. So smooth conformal isometry means that F is a diffeomorphism, but more than that, if you pull back G primed to G to M, then this is equal to G up to some overall conformal factor. So it's enormously powerful. You don't know anything about M and M primed. You don't even know they have the same dimension. Distinguishing means that so take M, for example, 2 points in M, 2 distinct points in M have distinct chronological futures and distinct chronological pasts. So you know nothing about F. You don't even know that it's a homeomorphism. It's just a bijection and it preserves the causal order. But if it does, then F is of smooth conformal isometry. So in words, it says that in the causal order itself, without any other information, is encoded the topology, including the dimension, the differentiable structure, and 9/10 of the metric in 4 dimensions. So if you know the metric in 4 dimensions up to a conformal factor, then you know 9 out of the 10 components. Okay, so I'm going to first of all tell you something which is relatively easy to prove, which is that if you replace distinguishing by strongly causal, then this theorem was proved by 1966. But the final strengthening, the final and most strong version was proved by Malamute in 1977. Okay, so in 1966, so what happened by 1966? Although this is 1967, I think these things were known by Penrose long before. So anyway, I'm pretty sure that these dates are a bit screwy, and that this result in 1966, by then this was known. You know, it's like one of these things that in maths, you know, you think, yes, it's known, and you say, well, who knows it? And you say, well, I don't know, it's just known, right? Okay. So Chronheimer and Penrose proved that the causal relation implies the chronological relation for any space-time. It doesn't have to be strongly causal or distinguishing or anything. It has to be causal. So for any causal space-time, the causal relation implies the chronological relation. Okay, so I'm going to show you that, because that is incredibly informative. It's very illuminating how you prove that. Right, so now this is all in the continuum, forget causal sets and discreteness. So let this symbol, which they call the Harasmus relation, it is a relation on space-time, equal the difference between the causal relation and the chronological relation. In other words, x, x points to y if x precedes y, but x is not to the chronological past of y. So in other words, it's the null relation, right? It's what's left over of the causal relation if you take away all the chronological, if you take away the chronological order. Okay.
You didn't write the null.
Thank you. Yes, thank you. So clearly, if you know the Harasmus relation and the causal relation, then you know the chronological relation, because if x precedes y and x does not point to y, so they're not null related, so they're causally related but not null related, then they must be chronologically related. Okay. So the proof, Chronheimer and Penrose's proof, is that the causal relation, you don't need to add the extra Harasmus relation. You can deduce the Harasmus relation from the causal relation. Okay, so let's do that. Right. Okay, so let's so think about example first. You'll see how it goes. And the example is just Minkowski space, any dimension. Let's do it in 4. I mean, let's not do it in 4 because I can't draw 4. Okay. So in Minkowski space, here is x, and here's the light cone, and we have a point y, and we only know the causal relation. We don't know anything else, and we are going to define, well, we have defined the causal diamond between x and y, but of course the causal diamond is just a null segment. It's just this, right? So this is a null segment, and it's linearly, it's totally ordered by the causal order, right? So it is totally ordered. In other words, it's a chain. All right, so it's a chain. Is a chain. Okay, so that's the key. So theorem. Oh, first of all, definition. X, H, Y. So H is this is a relation that I'm going to define. If and only if. So if any proper subinterval I of a proper subinterval I u v of I x y is a chain. Not only is the interval between x and y a chain, but any subinterval, right? You just take 2 points in between x and y. The interval between them is also a chain. All right, and then theorem, which I'm not going to prove because I don't have time. X, H, Y, if and only if X, arrow, Y, X points to Y. So you might say, well, why don't we just say that X, H, Y, if the interval between the X and Y is a chain, just as it is in Minkowski space? Well, this definition, so this definition deals with cases where you have caustics. So for example, if you have the 2D flat cylinder and X is here, then the null geodesics from X go around the back of the cylinder and say they meet at Y there, then the interval between X and Y is not the single null segment, but it's both these null segments. So that is not totally ordered. So, but nevertheless, Y is in the Harasmus of X, and you need to subtract Y if you're going to get the chronological relation. So if you just said I, X, Y is a chain, it wouldn't cover this case. But if you demand that every subinterval of the interval between X and Y is a chain, then that works, because every subinterval of the interval between X and Y either lies in one of the null, either lies in this null geodesic, or it lies in that null geodesic, and it is totally ordered. Okay. Right. So the upshot is that, so corollary, this implies the Harasmus, which implies that. So you only need the causal relation. Everything is subsumed within it for every causal space-time. So, so the corollary is this, but it's so much more than that, because it doesn't just tell you the Harasmus relation and the causal order. It gives you the actual local null geodesics. It tells you, it gives you these sets, these subsets of the space-time. It tells you, here's X, and then it tells you which of the one-dimensional subsets of the manifold are null geodesics locally. So there's a huge amount of information contained in the causal relation, and that is the key to this theorem. Okay. Right. So that's the Chronheimer-Penrose theorem. Then, of course, the Alexandrov topology, which you get from the chronological relation, so the base of the Alexandrov topology are the Alexandrov intervals. That is the manifold topology if M is strongly causal. And here, this is super nice because it's the Lorentzian analog of the result It's the Lorentzian analog of the result that the metric topology for a Riemannian space-time is the manifold topology. That was first, wasn't it? So in the Riemannian case, oh boy. In the Riemannian case, you can define open geodesic balls, and those open geodesic balls are a base of a topology, and that is the manifold topology. But in the Lorentzian case, the analog of geodesic balls is some horrible non-local, not horrible, a beautiful but rather terrifying non-local thing, right? So that all the points that are proper time epsilon from your point P lie on this hyperboloid of infinite volume, space-like hyperboloid of infinite volume that asymptotes to the forward light cone, similarly in the past, and then space-like distance there. And so in between these four surfaces of revolution, there is the ball. Well, it's not ball at all, is it? So ball. So it's highly, highly, highly non-local. And of course, that's all to do with the null structure, and because all the points along the null cone, along the cone, they're all zero distance from P, as we know. So there's something very non-local about Lorentzian geometry. And you might think, well, there's just no way that there'll be a Lorentzian analog of the Riemannian theorem, but there is. And it's that you don't have balls, but you have Alexandrov sets, Alexandrov intervals, the open intervals, the chronological intervals between 2 points. So you need 2 points. You can't do it with one. So the Alexandrov sets are Alexandrov intervals. They are a base for the topology, the Alexandrov topology, and that is a manifold topology in the case when it's strongly causal. Okay. And then Malamute's theorem. So this is Malamute's statement of a theorem by Stephen Hawking, which is that if F is a homeomorphism and F and F inverse preserve future directed continuous null geodesics, so they map null continuous null geodesics into continuous null geodesics, and the dimension of M and M prime is greater than 2, then F is a smooth conformal isometry. Okay. No. Okay. So you put those together, you have that if you have a causal isometry, well, first of all, you know if you know the causal order, you know the topology. So if you have a causal isometry, that's also a chronological isometry. This chronological isometry, then the topologies are the same. Then if the topologies are the same, well, you have the topology of them both. You know what you mean by homeomorphisms. And Stephen's theorem, the Hawking theorem, it's a sort of explicit construction of a differentiable coordinate system using the structure of these null geodesic segments, which you know because the Chronheimer Penrose construction tells you what the null geodesics actually are. Okay. Right. So Malamute strengthened this theorem, and in view of time, I'm not going to go through how that was done, but it's hard. I'll just point out, and I have to say, I've never understood it in the way of, you know, how sometimes you go through a proof and you say, yes, I understand this step and I understand this step, and yeah, this step is right, and that's surely right, and that's surely right, but the whole overall thing, you know, you just think, I don't know. I mean, I see how you get from here to here, but I don't know why. And that's kind of how I feel about this Malamute theorem. So the Malamute theorem, the heart of the Malamute theorem is that if you have a bijection between spacetime M and spacetime M prime that preserves future directed continuous time-like curves, then the map is a homeomorphism. And the hard thing is that if F and F inverse preserve all curves, like if they map future directed time-like curves to future directed time-like curves, and they map past directed time-like curves to past directed time-like curves, and they map continuous space-like curves to continuous space-like curves, then it's a homeomorphism, sort of straightforwardly. But you only know that this F and F inverse preserve the time-like curves, not all of them, not the space-like ones. It makes it hard, and I would say I struggle to have some intuitive feeling for why it is. So if anyone wants to tell me, that would be great. Okay, so finally, the Malamute theorem is that if you have distinguishing spacetimes, each with spacetime dimension greater than 2, you have a chronological isomorphism, then F is a smooth conformal isometry, and the Chronheimer, Penrose, Hawking, Malamute theorem is a corollary of this, because if you have a causal isometry, then it is a causal isomorphism, then it is a chronological isomorphism.
What's the obstacle in dimension 2?
The obstacle is everything holds apart from the Hawking result. So it's the construction of this coordinate system, this differentiable coordinate system. It requires that you have 3 dimensions. You can look at it and you see, yes, you need, it won't work in 2. So, yeah. Good question. I don't know. Yeah. Right. Okay. So I'm coming to the end. Give me 1 more minute. So the causal relation encodes the metric up to a conformal factor in the continuum. The causal relation is 9/10 of the metric, and it can't be more, of course, because if 2 metrics are related by a conformal factor, then their causal orders are the same. The light cones are the same. So the missing data is equivalently a local. So that the extra 1/10 that you're missing is equivalently a local scale, a conformal factor, 1 component of the metric or the volume measure, or the information which is the volume of every space-time region. So you can encode the result of this Chronheimer, Penrose, Hawking, Malamute theorem as saying that Lorentzian geometry equals order plus volume. And if you think back now to the discrete continuum correspondence, where you faithfully embed a causal set into the manifold, then if a causal set is uniformly embedded in the approximating M, then the idea is that the order of the embedded causal set respects the space-time causal order, and heuristically, the order of C gives rise to the causal order of M, and the counting measure of C gives rise to the volume measure of M. So it's just the number of elements in a region which gives you the volume of the region. And so discrete Lorentzian geometry is based on, based on this slogan, which is order plus number. Discrete Lorentzian geometry equals order plus number, which is based on, so that it's a conjecture, it's a hypothesis, it's based on this theorem plus the insight of Riemann that a discrete manifold contains within itself metrical information. Okay, so I won't give you the last slide, but I'm